how's it going? We have a little bit of catch up. I want to talk about a bunch of things. Um, Mostly, I want to talk about the ensembles of weak learners on this pre-video, but I have two other things I want to address. So, one of them is a leftover from support vector machines. Because I totally bombed on recording the pre-video for Wednesday's lecture, I want to just give you one little bit of mathematical definition on kernels that I would have had in that pre-video. So we already talked about kernels, you have some idea about them, but let's talk about their formal math definition. So a kernel it is essentially a weighted sum on some sort of function or integral, all right? And these kernels have certain properties that are related to the properties of metrics, which we already discussed, right? The idea that metrics have certain properties like symmetry and a triangle inequality. Kernels have these properties too. Okay, but beyond having a metric-like property, kernels are a very particular kind of function. They are a function that maps from one vector space. We're going to denote that x here. Okay? One vector space in a n-dimensional vector space, right? To another vector space that's in an m-dimensional vector space, where in general we're usually talking about the higher dimensional vector space being what we're mapping to. So, now, a kernel is a function which doesn't just map to some higher dimensional space, right? That's one version of a kernel. But a kernel also has this property that we can take an inner product in the original vector space and get some single number. That is, this is the dot product bit. Okay? There's essentially two different ways to look at kernels. Kernels either can be, well, I shouldn't say either. There are two different ways to look at the same thing. Kernels must both be able to be seen as a mapping from a lower dimensional to a higher dimensional vector space, where we can, just like we saw earlier, right? If we have a donut problem, that we can transform that donut problem into a three-dimensional picture that looks like this, right? Such that we can put a hyperplane separating it in 3 dimensions, right? That's the lifting map version of a kernel. Okay, but kernels also can be written as dot products. So this is an inner product, and a dot product is one kind of inner product, right? This is a version of the feature map has to be able to be written as a transformation of some data point x dot producted with a transformation of some other data point x prime. Okay? So this kernel has two different flavors, two different viewpoints of the same thing. One is the version where it is a feature map that lifts us up to the high dimensional space. And the other version where the kernel can also be written as a dot product in the original lower dimensional vector space. Okay? And when we have that, a dot product on a low dimensional vector space resolves into a single number, right? Dot products make scalars. So we only have to calculate the dot product on a low dimensional space, and it is equivalent to moving it up into a higher dimensional space like this. There are two equivalent acts, and being able to do both of those is what makes a kernel a kernel. Okay. So, carriage return, line feed, brand new topic. Let's talk about the idea of ensembles, because ensembles are what we're talking about this week. The idea of an ensemble is to take a bunch of separate machine learning systems that all make their own decisions, and we want to give them the same data. So start with a data point, give all these different machine learning systems the same data point. Each machine learning system has its own idea of how to classify that data point, and we do something to combine the ensemble of machine learners into a single answer. Oftentimes, this is just a majority vote. Okay? The reason we talk about ensembles at all is that it turns out we can mathematically prove that under certain conditions, an ensemble of learners is better than any single one of these guys. How can we prove that? Well, let's go take a look. Let's do it, right? So we're going to start from an assumption. We're going to assume that each one of these machine learning systems is independent. What does that mean? That means that if this one, makes a mistake on data point 1 and data point 3, this one doesn't necessarily make mistakes on the same one. Maybe it makes mistakes on data point 2 and data point 7, and this one makes mistakes on data point 3 and data point 9. That each one of them is independent in the sense that it is statistically independent. Whether it gets it right or wrong, that is statistically independent. It's not on like certain data points, all of them get wrong. Okay, so we assume independent classifiers. And each classifier has some error rate. Okay, more to the point, to simplify our math, what we're going to say is all classifiers have the same error rate. Now can be a very weak assumption, right? And that's what we want to get at is, given very weak assumptions, can we show that an ensemble of classifiers is better than any individual one? Okay, so let's take this in the case of a binary classification task, because that's our easy version. And what we're going to say is, not only are we going to assume that all the classifiers have the same base error rate, we're going to assume that error rate is just ever so slightly better than 50-50, right? So this error rate is going to be just a little bit under 0.5. Okay. In this formulation, we can use a formula that may be familiar to you. That's just the binomial distribution. Okay, that's the PDF of a binomial. And we can use it to show that the ensemble must be better than any individual. Okay, so we're going to start with a weak learner which is just barely better than chance. And we're going to show that putting together enough weak learners is going to be arbitrarily good at getting this thing done. Okay, let's go back to our idea here, right? If we formulate this, how we take an ensemble and get an answer out, we formulate it as the majority vote. That is, if more of these learners say this is a positive class instance, then we're going to say this is positive class at the output. Okay, that positive class, how many of these things we need, that is the key here. All right, so if we need to have the ensemble be correct, then we're saying out of n possible learners, at least half of them, k, right? We're going to say k has got to be greater than the number of learners divided by 2. This is the criteria where the majority vote is correct, right? if we can take n learners in our ensemble and at least k of them are correct, where k has to be greater than half of the learners, then we know that the ensemble itself is going to be correct. So what we've got to do is we've got to take k from starting at n divided by 2, starting at half of them, and running it all the way up to all of them being correct, right? And that's going to be the ensemble error. That's going to be the error rate of the entire ensemble. Because what we're saying here, if let's say that we have 11 classifiers, right? So n is equal to 11. And let's say that on average, each of those classifiers makes 25% mistakes. That is, it's 75% correct. Then the binomial theorem says that if we plug in the error rate for the individual, right, and we calculate for k equals to 6, which is when we just have a majority criteria. 6 is bigger than 5.5, right? So we get 6 voting the correct way. We calculate the binomial probability for 6. But then we would also be getting the correct majority vote when we had 7 and 8 and 9 and 10 and 11, all 11 of the classifiers voting the correct way. So we just have to add up the binomial PDFs for all of those cases. 6, 7, 8, 9, 10, and 11 of the 11 classifiers voting correctly. And that's the total probability of those mistakes being made by all of those, right? Of all 6 making a mistake, all 7 making a mistake, all 8 making a mistake, all 9 making a mistake, all 10, all 11 making a mistake. That totals out, when you do the sums on the binomial, to a 3.4% chance of an error. In other words, every other situation that those 6, 7, 8, 9, 10, 11 ensemble machine learning classifiers will make is right. We are going to end up with, what is this? 96.6% chance of a correct ensemble prediction when we started with each one of them only being 75% correct. I hope I did my math right there. I think that's right. Okay. So an alternative way to look at all this is to look at this as just the law of large numbers. When we get enough samples on any random probability distribution, we know the average of the probability distribution. Okay? So if you have a coin that is just barely biased, like a 51% heads coin, if you do runs of flips, hundreds, thousands of flips, on average, that you will be able to eventually see for different runs, right? Each run, when you have just a few flips, you don't really know if the coin is fair or not, right? When you're over here in this regime where you have just a few coin tosses, But when you do long runs, that is, if you think about this as if you have lots of learners voting, right? Then you are going to be able to see a coin that has just a single % of bias towards heads eventually. So this ensemble math is exactly that law of large numbers. Okay. What it means for us is that if we have a base rate error shown by this dotted line, okay, the base error here. So when the base rate error is 0.4, that's just better than chance. Then an ensemble is going to have a curve that looks like this blue line for a particular number of learners in the ensemble. And the more the learners, the steeper the sigmoid gets. Okay, so that's like a large number of learners in the green. Okay, and a relatively small number of learners will be a little bit shallower. Okay, so the more learners you get, the steeper it gets. So if you get an arbitrarily large number of learners with just barely better than chance, you can still get nearly perfect performance on classification. Okay, I told you we were going to cover a lot of different things today. And this is the last one. I want to get you ready for us to discuss something during the class where I actually show you the bias variance trade-off derived in mathematical form. Okay, so to understand this, we need to understand the nature of expectation calculations. Maybe you remember this from your stats class, but when we're looking for expected values are denoted by this E, right? So expected values have some mathematical properties. Like, for instance, the expected value of a constant is just the constant. The expected value of a constant times a random variable x, you can just pull that constant outside the multiplication and multiply it by the expected value of x. Expected values of sums of random variables are just expected value of x plus expected value of y. However, the product of random variables, if they are independent, means that you have ex times ey, but only for the case where x and y are statistically independent. Okay, just that reminder can help us understand how the derivation of the bias variance trade-off works. Let's talk about this idea. What we are talking about here is that y is the true measurement of something, or it's the thing that, we have the labeled data for. Okay? Reminder that hat means an estimate, right? This is our machine learning system. After we have trained it, this is our prediction of the machine learning system. So that's our ML prediction. So what we're after here is quantifying how bad are my errors going to be, right? The truth minus our prediction. What is the expected value of that error? And more to the point, we're formulating this right here as a squared error. So we're talking about what is the mean squared error of our machine learning system? What is the expected value of that machine learning system? Okay? So this here, the expected value of the machine learning system, well, we can break it up into parts. So let's start with this. Y is equal to f of x plus some epsilon, because, this is just the assumption that statistics exists, that we have some true value f of x plus some noise that it's corrupting that true relationship, right? This is just statistical ML. I should write statistical machine learning, right? It's just that there's some true value here. The y value that we measure is some true relationship corrupted by noise. Okay. Now we can start using these properties of expectation to do a little bit of algebra. First things first, these are additive terms, so we can pull any one of these terms out. Like this epsilon here is going to go outside over there. All right? Then we can start doing some algebra and end up, dealing with this, polynomial and expanding it out. And we end up in this situation here. All right, you can do a little bit of simplification, get it down to here. Because again, this epsilon here, that's a constant, right? So we can pull it outside over here. All right, what we have done at this point is we have said, hey, the difference between our measured value and our prediction, that expected MSE, we can get rid of the epsilons, right? We can pull the noise of measurement out into separate terms. So there are two noise terms here. Noise term number one is the expected value of the noise. That is, it's just the standard deviation or the variance. Well, okay, so it's epsilon squared, right? So it's the variance of the measurement noise. So this is just the measurement noise irreducibly. This measurement noise can never go away because it's just part of the process of measuring these y's. This is the expected value of the noise. So this is the variance. This is the mean of the noise. And by formulation of statistical learning, noise is zero mean. Okay, that's just this formulation of statistical ML. Noise that has zero mean but some variance. Well, that's zero. So this entire term goes away. That's nice. So we get down to this. We can just care only about the irreducible noise of the situation and the difference between the true relationship and our estimated relationship. Okay, ready? Let's do more. Because we can take this one and break it down further. So that's what we're going to do over here. So here's that thing, the difference between the true relationship and our estimated relationship. The mean squared error, the expected value of that mean squared error. Okay, this is where I confess to you that this is where the proof goes places that oftentimes proofs do, where I would never think of this myself because I'm not a real mathematician, but we can just talk about what's happening. So the first thing is, like with a lot of math, we do some careful manipulation to allow us to break it apart into components. So what we end up doing is we end up adding and subtracting the expected value of our machine learning estimate. Well, what does that mean, right? In fact, what should we even call these expected values? I should note that what we're talking about here is we're talking about the expected value over lots of different training sets. So different training sets, right? We have a particular sample of the true population. That's become our training set. If we had a different sample of the training of the population for our training set, we would get a different estimate from our machine learning system, right? So the difference between the true relationship and our machine learning system's prediction is going to be different for different training sets. So we're averaging over different training sets here. That's the idea. On average over different training sets, what do we see? That's what this big E is. Okay? So the manipulation we're making is we're adding and subtracting this expected value of the machine learning system's estimates on average across different training sets. So we can plug that in here where we put those terms in each of these two terms. We can do some expectation algebra using the the rules before, where we can say if, for instance, here, the expected value over expected values, right? Well, the thing is we can get rid of this exterior expected value because this is a constant in here. It's a constant because this is a constant. It's the true relationship. It's not a random variable. And this is the mean of the machine learning system instantiated over lots of different training sets. So this is a constant because it's a mean. So a constant minus a constant is a constant. So here, this term, we can just take the interior and get rid of this expectation. Okay? So, like I said, there's a lot of different manipulations here. But in the end, what we can see is once we've got it to this level, you can understand that this term here, this is the bias in the machine learning system. This is the difference between the expected average over many training sets of the machine learning prediction and the true relationship. That is, it's the bias. Are we continuously underestimating or overestimating the true relationship? That would show up here. Okay, this term is the variance. How do we know that? Well, it's the expected value of our one particular estimate minus the mean value of estimates over many training data sets. So that's the definition of a variance, right? A particular measurement minus the mean squared, normalized, right? That's a variance. So this is the variability from fit to fit, this being the particular fit of the training set, right? This is the difference in the variability of what the parameters are going to be. Right, so this is the bias term, this is the variance term, there's this other thing here, right? And it turns out that this other thing is something that we can fundamentally ignore, right? Because we also have essentially a constant here, right? Because when you get it down to this form, not only is it a constant, but this term is this minus the same thing, that is, that goes to 0. So this whole term drops out. All right, so this is equation 8. We have shown that this is just the bias in the fit, right? The difference between the average fit over many training sets and the true relationship. And this is the variability in the fit, right? A particular fit, how different is it from the average? What is the average difference between a particular fit and the average fit? Okay, so that equation 8, we just have to combine that with what was on the back side, right? If I go back to that last slide, right? We have this stuff here, which is what we just did in equation 8. And we have this fundamental noise, the variability in measurement noise. So what you can see is that's the sigma e squared, right? That's the irreducible error, the measurement error. So you can see the average error of a machine learning system, the average mean squared error over many different training sets, is got some unreducible error that we can never get rid of. And we have a term that's bias-oriented and a term that's variance-oriented. And so this is the mathematical derivation of the bias-variance trade-off. Because for a given level of performance, this is a constant, this is a constant, So given a level of performance, of predictability, we can only ever trade off where that error goes between the bias term and the variance term. All right, that sets us up. Now you've seen the whole derivation, you've seen a bunch of stuff. Thank you for putting up with this extra long pre-video. I hope to see you on Monday. Bye.